In this video, we're going to review some of our integration techniques. Thought I'd start off with a very basic one, where we can just use the power rule. And let's do x cubed plus 5x squared plus maybe let's throw in a negative and fractional exponent in here. So let's say that we have that. We don't have to have parentheses, but if you like parentheses around there, you can. We're just going to apply the power rule. So the antiderivative of x cubed, we raise the power by 1 and then divide by that new power, or make it a fraction out in front. Either way. Remember that when you take the derivative of this, you should get that back, right? That's what an antiderivative does. So the derivative of 1/4 x to the 4th would be 1x cubed, which is what we get. All right, raise the power by 1, divide by that new power. For this one, I would be thinking, we can do this in our head, we can think of that as x to the negative 1/3 power. It's x to the negative 1/3 power. So our new exponent would be x to the, we raise the power by 1, and negative 1/3 plus 1 is 2/3. And then you divide by 2/3, which is the same thing as multiplying by 3/2. And then we don't forget our constant of integration. So quick review of the power rule. Let's do this one. Let's do the integral of x over square root 2x squared minus 1 dx. Okay, so for this one, we're going to use a little u sub. So I'm going to come off to the side. I'm going to let u be what is inside the radical in the denominator, and then du will be 4x dx. I have the x dx, so I need to move the 4 over, right? So 1/4 du is x dx, and now I can replace x dx with 1/4 du. Replace that. Okay, and in here inside this radical I have the square root of just u. So this becomes the integral of 1/4 du. I can move the 1/4 outside. 1 over square root of u du. And now we're back to something that we can use the power rule on. So again, I'm thinking of this as u to the negative 1/2. So we'll have 1/4. U to the, raise your power by 1, divide by the power, plus c, and then last step is just to go back to your x's. So 1/4 of 2 is 1/2, and then we'll have the square root of 2x squared minus 1 plus c. Okay. 3. Let's do this one. What if we have something like this rational expression? So when you see a rational expression, you should look at the power of the top, power of the bottom. If the power on the top is greater than or equal to the power on the bottom, you always go off to the side and divide. So I'm going to go off to the side and divide. We're going to divide x plus 2 into the numerator. And we can use long division here, or in this case, we could use synthetic division. Synthetic division, if I can use it, I will always use it. So with synthetic division, we put negative 2 into our box. Goodness. Into our box. And then up on top, we're going to put our coefficients, beginning with a 1 for the x cubed, a 0 for the x squared, a 0 for the x, and then a negative 1 for our constant, right? Bring down your 1, multiply and add, multiply and add, multiply and add. So our new, when we divide this, we have not integrated yet. When we divide, we started with an x cubed. This will be the coefficient of the x squared term, so this will be 1x squared minus 2x plus 4. The negative 9 is our remainder, and that goes over our denominator there. And now we're back to the power rule for all but this last term. Power rule for all of these, last term will be a little natural log. So power rule, 1/3 x cubed minus x squared, right, plus 4x. And this is a little natural log because if you take the derivative of that denominator, you get just 1, right? Just 1. Remember that it's going to be a natural log as long as when you take the derivative, you don't get an x left. The derivative cannot include x's. If it does, it's not a natural log. You have to do something else with it. So minus 9 ln absolute value x plus 2 plus c. Okay, let's take a look at this one. Number 4, let's say we have integral of dx over 1 plus 4x squared. Okay, you have this. We need to, first of all, you cannot do a u sub. We cannot let u be the bottom because du would have an x in it and there's no plain x on top. So we cannot do a little u sub here. This is an arctan. This is an arctan. U will be the square root of your x expression, so 2x. A will just be 1. It's the square root of your number here. Du will be 2 dx. So there's our dx. Divide the 2 over. So I'm going to replace dx, replacing dx with 1/2 du. And then here I have u squared, and here I have a squared. That is straightforward arctan. So 1/2 from that, 1/2. For arctan, you need a 1 over a, but in this case, a is just 1. Arctan, u over a plus c. Squeeze in your plus c. So this would be 1/2 arctan of 2x plus c. Okay? Next up, what if they ask you to find an antiderivative of x minus 28 over x squared minus x minus 6. What if they ask that question? How do you find an antiderivative? Well, an antiderivative is the antiderivative of this. So you just are taking the integral of that with respect to x. So I need to find the integral of that expression with respect to x. So we have this. Can't divide. It's not. We can't do a u sub on the bottom. Okay, so I'm going to go off to the side. I notice that the bottom can be factored, so I'm going to go off to the side, and we're going to break that into its partial fractions. So we're doing a partial fraction decomposition. We can factor that into x minus 3, x plus 2. Be careful factoring. Is equal to, and then we have something over the x minus 3 plus something else over the x plus 2, and we find these two partial fractions, and then we can easily integrate those two. Multiply both sides by the common denominator. So x minus 28 is equal to a times that x plus 2 plus b times the x minus 3. That's what you get when you multiply both sides by that. We can let x be anything we like. I'm going to begin by letting x be a negative 2. If I let x be negative 2, I have negative 30 on the left side. This piece is 0, and then I have negative 5b, which means b has to be a 6. If I let x be 3, then 3 minus 28 is a negative 25 is equal to 5a, and then this piece will be 0, and that gives us that a is a negative 5. So I can put these pieces back. So this integral is now a over x minus 3, so negative 5 over x minus 3, plus b over x plus 2, and now we have two little natural logs. Negative 5 natural log x minus 3 plus 6 natural log x plus 2 plus c. Okay, next piece of scratch paper here. Okay, number 6. Let's say that we have this 2 on top, and on the bottom, let's say we have x squared plus 4x plus 13. This looks similar to the previous problem. However, the denominator cannot be factored this time. So if it cannot be factored, then we need to force it to be an arctan, right? We force it to be an arctan. So to force this to be an arctan, I'll leave my 2 alone. If you want to, you can pull that 2 completely out. So we'll have x squared plus 4x, right? To complete the square on this, we add half of this term squared, right? Half of the 4 squared. Half of 4 is 2, squared is back to 4. And then we need to keep our 13 here, so what do we add to 4? To get to 13, we need to add 9. I think I will take that 2 out. Factor this, and it will factor into a perfect square binomial. I know it will factor into a perfect square binomial because of what we did to get that. It has to be. So x plus 2 squared plus 9. So this is an arctan. Oops. U is just the x plus 2. A is 3. Du is just dx, so we don't have to multiply in anything else. So the 2 from the top, and then don't forget with arctan, you need the 1 over a, arctan u over a plus c. So that was one done by completing the square. Okay, next up, let's try this one. Okay, for this one, I see that I have an algebraic function multiplied by a transcendental function, and I cannot do a u sub. If we let u be 2x, du would just be a 2, and we have these x cubes over here, so that will not work. Cannot just do a u sub. But I do have a transcendental times, an algebraic times a transcendental. So that's one of my signs to do a biparts on it. And since it is an algebraic times a trig or an e function, I'm going to use the tabular method. So u and dv. Under u, I'm putting 3x cubed. Under dv, I'm putting everything else. Okay? We take the derivative of u until we get to 0. So 9x squared, 18x, 18, and 0. Keep taking the derivative until you get to 0. For this side, we need to take the integral of each piece. The integral of sine is negative cosine. But remember, we have that 2x there, so we need to, the derivative would be a 2. We need to undo that 2, so it's going to be 1/2 a negative cosine of 2x. Right? The integral of cosine is positive sine, but we need to keep that minus, so minus, don't forget to undo that 2 from that, so it'll be 1/4 sine 2x. The next integral will be positive 1/8 cosine 2x, and the last integral here will be 1/16 sine 2x. Okay? I know we multiply diagonally. Don't forget to change these signs here. So keep this positive, make that negative. Positive, negative. We alternate starting with positive. And now we can just come and write our answer out. Positive 3x cubed times negative 1/2 cosine of 2x. That'll be a negative 3/2 x cubed cosine 2x. And then go to the next piece. Negative times a negative is a positive. 9/4 x squared sine 2x. And here we'll have positive 18/8 x cosine 2x, and then negative 18/16 sine 2x plus c. Okay. What about this one? What about that one? Need to do by parts on this? But this is not a table one. Okay? It gets complicated if you try to do a table on this. So I would just take it in its pieces. Let u equal. So if we have a natural log, that's what you need to let u equal, right? Let dv be everything else, the x dx. Du, the derivative of natural log x, is 1 over x dx. And here we're integrating. V will be the integral of x, which is 1/2 x squared, plus c, but we're going to take care of the c later. Okay? All right. So now we multiply u times v, so 1/2 x squared, natural log x, that's uv, minus the integral of v du. So when I multiply v times du, I'm going to have 1/2, which I'm going to pull outside my integral, and then I'm going to have 1 over x times x squared. 1 over x times x squared is just x, and then we have our dx. And now we can use a little power rule on that. So that is 1/2 x squared plus c. So if you wanted to, you could change that to a 4th. Okay, number 9. What if we have this? Integral of x sine of x squared dx. What process do we use here? Don't get tricked into using by parts here, because you cannot use by parts here. This is not a by parts problem, because you would be needing to take the integral of sine of x squared. And what is the integral of sine? Let me come over here. What is the integral of sine of x squared? We need a Taylor series to do that, a Maclaurin to do that. So that's a complicated, it doesn't look complicated, but it really is complicated. So since we would have to do that if we were doing by parts, don't do by parts on this. This is just a little u sub. U is x squared. Du is 2x dx. We have the x dx. So 1/2 du is x dx. So I'm going to get from that 1/2 integral just sine u du. That is something we know the antiderivative of. And then just go back to x's. So don't always go to by parts if you have an algebraic times a transcendental. Always try a little u sub first, always. Okay. All right. Next up, I'd like to do Next up, I'd like to do a little, what if we have this improper integral? Integral from 1 to infinity of 5 over x to the 4th dx. Well, it's improper because we have infinity as one of our boundaries, so it's not really a boundary because it's unbounded, okay? All right, first of all, before I even get started, let's think back when we were doing series and we had this thing called the integral test. Do you remember? We said that this integral, the integral does whatever the series is doing, as long as this expression, this function, is positive, continuous, and decreasing, which it is. So this integral does whatever the series does. What does that series do? You guys can all look at that, and you know it's a little p series, and you know it converges because p is greater than 1, right? My pen just ran out of ink. Let me grab another pen here. Okay. All right. So I know that this converges. And so you can look at this and say, gosh, I know that that thing converges. It goes to infinity. I know this is going to converge because it behaves just like this. That doesn't help you evaluate it, but it's good to know that this does not diverge. Okay? Does not diverge. So we're going to go ahead and take the antiderivative. Take the antiderivative, the 5. If you want to bring the 5 out, you can. I'm going to rewrite this as 5x to the negative 4. That's what I would be thinking in my head, right? I'm going to leave a space because I need to put something there. Leave a space. This is going to be 5 times, all right, x to the add 1 to the exponent. Add 1 to the exponent and then divide by that exponent, right? Now I want to put 1 to infinity. The 1 is fine. The 1 doesn't change anything. I do not want to put infinity as a boundary. When you put a boundary here, it has to be a number. And infinity is not a number, it's a concept. So what I'm going to do is call that b, and then out in front, take the limit as b goes to infinity. I'm going to pull out that negative 5/3. Just pulling it out. And then I'm going to rewrite x to the negative 3 as 1 over x cubed. Okay, now we put b in for x and let b go to infinity. Put b in for x, let b go to infinity. So we'll have 1 over an unbounded number, so that first piece will go to 0. So we'll have negative 5/3 times 0 minus, now we put 1 in for x, and that's just a 1. So this is 5/3. Let's take a look at this one. 2 to infinity of this. Well, if I do what I did just now, before I just dive into the antiderivative, if I do that, let's go off to the side and take a look at the series. What does the series do? Well, the series acts like 1 over n, right? That's what it acts like, which we know diverges. So I know that this integral will diverge as well. The function is positive, continuous, and decreasing on these values of x. So I know that this will do whatever the series does, so I know it's going to diverge. Let's go ahead and show that with the integral. By the way, that would be, if you wrote that out, that the function is positive, continuous, and decreasing, therefore it converges or diverges as the series converges or diverges. You're using the integral test, and since the series diverges, this must diverge. by integral test. Okay, anyway, most of you would probably just dive in and take this antiderivative though. It's not that hard, right? So the antiderivative here, if you look at the denominator, the derivative of that is 2. We have to undo that 2, right? Undo that 2, and then it's just a natural log. And we need to evaluate that from 2 to infinity. So again, get your notation right. Now we're going to begin by putting b in for x and letting b go to infinity. We'll get something going to infinity here, and then the natural log of something going to infinity is infinity because we know what the curve natural log looks like. Yes, it gets to infinity slowly, right? So this will be infinity minus, and then when you put 2 in for x, we'll have 1/2 natural log of 3. This is infinity, so the integral diverges. Just like we expected. Number 12, integral 0 to 3 of 1 over x minus 3. This looks so simple. Why do I have it here? Right? Why do I even have this here? Well, I have this here because the graph of this function has an asymptote, a vertical asymptote. This has a vertical asymptote at x equals 3, and that's our boundary. So this is an improper integral, even though at first glance you may not see that. Okay? So be careful with that. So this is going to be, so the antiderivative is just natural log x minus 3. We want to go from 0 to 3, but we can't go to 3. We can go to some letter and then let that letter go to 3. Okay? I can't put 3 there because it makes my original function undefined. So you can't put a boundary that makes your original function undefined. So now we can put b in for 3, let b go to 3. If we let b go to 3 and we're coming at b from the left, we're coming at 3 from the left, right? So b is going to 3, so this is going to 0. This is going to 0. And our little natural log graph, what happens as x goes to 0? As x goes to 0, y is going to negative infinity. So this is going to negative infinity minus natural log of 3. So this diverges. This integral diverges. Okay, one more. Negative 3 to 5. Okay, why is this one here? Well, we have a vertical asymptote at x equals 0 this time. And 0 is inside of our boundaries here. So we need to split this up into 2 pieces. Negative 3 to 0 and 0 to 5. And take each piece individually. Okay? I could make this more interesting. Let me make this more interesting. Let's make it x squared on the bottom. Let's do that. Still has that vertical asymptote at x equals 0, right? Okay, so now let's see. Antiderivative, it will be negative 1 over x. I want to evaluate it from negative 3 to 0, but I cannot put a 0 there, so I'm going to put a b. We're specifically coming at 0 from its left because we're approaching it from the negative 3 side. And then here we're going to have negative 1 over x from, I'm going to call that a to 5. where a is going to 0, this time from its right because we're on the side of 5. Okay. Now, put b in for x and let b go to 0. Specifically from the left, right? So from the left it's going to be negative still, and it's going to 0, so that piece there is going to infinity, right? That's going to infinity, positive. Minus 1/3. Since we got that for that limit, we don't even need to go over here. Since we got that this one is going to infinity, we don't even have to go over there. This diverges. Okay, that diverges. Okay, that was just a quick little recap of some of our integrals. I'm sure I missed something. I feel like I missed something. But anyway, quick little recap. Now it's time for you to go try some of those in our integration review worksheet.